Hi, I'm going to talk about the distribution of sample proportions. Now, previously, I've already touched upon the distribution of a sample mean given a larger population that you're pulling that sample from. And then I also talked about the distribution of the difference between two sample means from two different populations. And I also showed how we can use that to test a hypothesis about a population, whether two different samples were pulled from two populations that were representative of a single population in terms of whatever metric we were measuring the average for. Now I'm talking about sample proportions. Sample proportions are very similar to the average, very similar in how we can use them. But with a proportion, we're looking at success or failure. Just like when we looked at the binomial distribution, we were looking at the number of successes given a number of trials. Well, if we take those number of successes and we divide by the number of trials, we're getting a proportion of successes. When we use the binomial distribution, though, we're just looking at the number of successes. We can actually use what I'm going to talk about to estimate the binomial distribution. This is possibly preferable sometimes to even what I told you before, basically estimating, it depending on how large the number of trials are. This could be also useful for estimating a binomial distribution if you look at it in terms of proportion. So I'm going to go ahead and explain how we do this. So I use F here. Actually, I don't know if I even used it, but F is the frequency of a characteristic among members of a population. So if you have a larger population, even if you want to think about coin flips, 50% of them are heads, 50% of them are tails, even though just you're looking at a coin and you just keep doing trials with that coin. But if you want to think about it that way, and when you take one head away, there's still just as many heads and tails as there were before. You can kind of think of it that way, or even with dice. If you want to think of the 1, 2, 3, 4, 5, and 6 as always being represented the same amount with replacement, basically, even if it's without replacement in other aspects, it doesn't matter because that population size is so large compared to your sample size, yet your sample size is still large enough to make an inference here. So frequency is how often you see it. The probability of seeing that characteristic is the same as the frequency. And X, with the binomial distribution, this is a little bit confusing because I used X in the context of an actual outcome for one member of a sample, like one of the ones in a sample, which is a member of the larger population. And I use that as the value that it has. In this case, though, with the binomial distribution, I've already showed it this way, and I'm showing it this way again. X will actually just be the number of successes, successful trials of n trials in a sample. So imagine that all your trials are just one sample out of a larger population. And the probability of success is the same as the proportion in that larger population of successes, and you're just pulling them out to see if it's a success or a failure. Because that's another way to think about it. They're pretty much the same kind of thing. So if you think about it that way, it's pretty much an analogy of pulling something and finding out if it's what it is already, even though it's already what it was before. You're not actually making it become that way by flipping a coin or rolling a dice, but the same math sort of applies. So though when you see X, that is the number of successes out of n trials. N trials, you could kind of think of it as the sample size, because really it is when you're using the math here. When you see P with a little, I don't know what that is, like an exponential character on top of it, that is actually the proportion of your sample. So if you want to think about it in the terms of the binomial distribution, that would be the same thing as X over N. That is the proportion of successes, the proportion of a sample exhibiting a characteristic. In this case, that characteristic is success, because that's what we're looking at the proportion for. We want to know how many are that way out of that much. And we use that as a decimal or a fraction of that sample. Just like P is a fraction or a decimal of the actual larger population. When you see sigma squared, lowercase sigma squared, that is the variance, as I showed you before, which basically you add up all the differences between each possible outcome, or at least each member of the larger population. If you were to take each one and compare it to the average of that whole population, you would subtract those, find the difference, whether it's positive or negative, it doesn't matter, because you square that value, you add all those squared values up, and then you divide by the number of members of the population. Or if you're doing it for a sample, it would just be the sample size. So P is the proportion, we were talking about the variance. The standard deviation is sigma, lowercase sigma again, and the standard deviation is the square root of the variance. And whenever you see z, I didn't use x here because I don't want to be confusing, because the last time I used x minus the average. But another way to think about it, basically what this is the observed deviation from what was expected. When we were looking at averages or just values, when we had an average, an expected value, that's another way of saying average, because you expect that more than all the other values. You take that difference and then you divide by the standard deviation. That standard deviation, once again, you compute the variance and you take the square root of it. Now with the binomial distribution, that actually is, so the variance is n times the probability of success times 1 minus the probability of success, which is the same thing as, so you're taking those two probabilities and multiplying times each other. Because when you go through that whole set of possible x's up to n, you're going to have values that are a mirror image of each other in probability. Basically what ends up happening is you're basically multiplying to get the standard deviation, to look at the proportion, we're going to end up taking just the probability times 1 minus the probability to get the variance. Then the standard deviation of that will be the square root of this, which I show here, p and 1 minus p, because we don't care about n, we don't actually care about the number, we just care about the proportion. And the proportion is going to be the same thing as the probability, because this is with the population. So the binomial distribution sort of mirrors the proportion in the fact that you're looking at the probability of getting something or the fraction of something, and that fraction actually determines the probability if you're thinking about it as a binomial distribution. So if you were thinking about p to the x as that proportion, all those values that are giving you a success, what you're looking for, and then 1 minus p as the other proportion or fraction that are not exhibiting that characteristic, you could still think about it in this way. So we're going to use the binomial distribution to derive what we need to derive down here, mirroring what I talked about for averages. So we could find the probability of getting an average given the actual average of the population. Only in this case we're dividing by n basically, because the expected value for the binomial distribution is p times n. Where did I put that? Oh yeah, right here. So the average value of the number of successes should be the number of trials you're doing times the probability of getting that success. So p, the probability, is like the proportion, the larger population of all of capital N of the population size. So if you think about it that way, only in this case, if you're looking at the actual population, it would be n, because that's the population size, times the probability or the proportion of that larger population. That would give us that's actually the number of, if you want to think about it, it's kind of theoretical, especially with the binomial distribution, but that would be how many of those we have out there. That would be, this would give us the actual proportion, but if we took the number times it, that's the number of ones out there that have the average that we're looking for. So the expected value is that. This gives us the average, basically the average of, actually I don't know if we should think about it that way. Scratch what I said, okay? But for the binomial distribution, the expected value is the number of trials times the probability of success. So the variance, as I said, for the binomial distribution, the variance of x, the number of successful trials, is the number of trials you're doing in that sample, in that test, however many times you're flipping a coin or rolling a dice, times the probability of getting something you're looking for, whether it be a 6 on a dice or a heads or tails on a penny, times 1 minus that probability of success. When we take that, this is looking at the spread of it, basically. The probability of getting it versus not getting it. If you were to have a probability of 0.5, like with a coin, you would have the highest variance possible. And if you really think about it, it'd go either way, right? So you're gonna have a lot of variation in your numbers, because you could have like a bunch of trials, but you don't know which way it's gonna tip on each trial. So that's when you have the most variation. The highest variance is when the probability is closest to 0.5. So if you're looking at the standard deviation, that is the square root of the variance. And so we take the square root of n times p times 1 minus p. Now, if we're looking at a proportion, though, we don't care about the actual number. So we need to divide out the sample size, basically. So if we do like 30 measurements, we got to divide that number of successes by 30, and that would give us our proportion in that sample of size of 30, for example. Now, so if we look at the actual variance for the population, when we're looking at a proportion, we would take the probability of each member being what we're looking for, what we're finding the proportion of. Then we would take that times 1 minus p, because really this derives from the binomial distribution. Because remember, a proportion, we're taking the actual value of the number of cases we found for this proportion, and we're dividing it by the number in that sample. So we can divide out n, so we basically divide out n to get the variance of the proportion. Of the population, basically. So when we take this, we divide out the n, or if you want to think about it as the larger population, be capital N. If it's the sample that we're looking at, then the actual variance of the sample itself, of the actual proportion, we would take p times 1 minus p. Now the variance of sample proportions, here we're taking that variance that I just talked about there, and we're dividing it by n to get that. We're dividing by n this time, though, simply because, remember when we looked at the averages before? We would divide by n to get the variance of the average of averages that we get. Sorry, the variance of averages. I don't want to be confusing. So in the same way that we did that to find the variance of a mean, we can also do the same thing with the proportion. It's just the same, it's kind of the same concept, but we're dividing by the actual number we already had first. So we already had n here, we divided, now we have p times 1 minus p, which is this right here. So the p times 1 minus p is here, and then we're dividing by n. So now what we can do the same thing we did before to find the distribution of a mean, but we could do it with the proportion. So instead of this being the mean of our sample, this is the proportion of our sample, and we're subtracting from the expected. What is the expected for that proportion? Well, it is the probability of getting one of those in the whole population, because you're taking that all the number of all of them in the population that have that characteristic, and you're dividing by capital N, the population size, to get that p. So we're taking the proportion of our sample, we're subtracting from the probability, which is the same as the proportion of the actual entire population out there. Just like we were subtracting the actual average of the population, we're subtracting the proportion because we're looking at proportions. So we can subtract that probability, and then we divide by, since we have to have a standard deviation down here. Remember, z is the observed deviation from the expected divided by the standard deviation. Now we're going to take the variance and we're going to take the square root of it. We already said that the variance the variance divided by n. Because remember, we also had to divide by n, because our sample size, as our sample gets larger, that variance gets smaller and smaller. So we divide by n. But to get the standard deviation, we got to take the square root of this. So we take the square root of whatever the variance is. We already determined that the variance is this divided by n. So we just have this part here for the variance. Then we divide by n, and we take the square root of that. So this, now we can get a z value for our actual proportion in our sample compared to the actual regular, the whole entire population, what we would expect. And we can look at the actual normal distribution now, and we can look at that z value in terms of standard deviations, which is what a z value is. That's the number of standard deviations away from the expected proportion, the p there. How far away is this from this, and in terms of standard deviations? Then we can compute the probability of having, if it's greater than the probability, we can take and find the probability of having that value, that proportion we got, or greater. When we find that, we subtract it. When we find that, we can determine the probability of us having that proportion, drawing randomly from the larger population when we do this, to find that z. Now, what if we want to find the probability of having a difference of two proportions, even from two different populations? So it's the same as what we did before to find the difference of two means from two different populations, the two different means for a sample from two different populations. We do the same thing, we just basically substitute this here, that's got to be this right here instead of what we had before. So we would be taking, we subtract the proportion 1, we subtract proportion 2 from proportion 1, then we subtract the difference of those expected proportions from the whole population, which is the probability minus the probability. We take that, and then we divide that by the square root of the variances of each added together. And those variances, we still have to divide by that n, because we have a sample size now, and that variance is smaller, and it's proportional to the actual sample size in comparison to the actual variance of the larger population. So we add those together, we take the square root of that, we get the standard deviation here, and when we do that, we still get a z value. We get a z value, though, for having that difference in proportions instead of the difference in means, like I talked about before. Then again, we can plug that in, and we can compare it to the expected proportion, and the expected difference of the proportions. And we can still see, is that really representative? If we wanted to look at it like we take two samples from two different populations, and we want to know, do those other two populations really represent each other? Given how much of one they have compared to the whole, versus how much of this one, of that same characteristics compared to the whole, are they still the same proportions in that population? We can take those two, and we can assume that population 1 is population 2. We can subtract those, get 0, and we're just looking at the difference of the proportions that we got in those two different samples. Then we can divide, and then we can use, if we have the same n, then we can use the same n and add those together. If they're different n's, that's fine. As long as we know what the actual standard deviation is in each of the populations. Like before with IQ, we looked at it and we said the standard deviation was 20, we had 130 minus 110, and then we subtracted 0. We can still do that, though, with if this is a proportion problem, like half of them and then 3/4 of them, and so you get it. So basically, we can do the same thing, and we can find the probability of having that difference. And if it's less than 0.05, we can confidently say, at least with 95% confidence, that those two populations are not the same. If it's less than 0.05, to have that difference in terms of probability. So I hope you enjoyed this, and thank you.